All right, simplifying radical expressions. So because 4 squared is 16, 4 is what we call the square root of 16. Okay, that should be fairly easy. What's the square root of 9? 3, what's the square root of 25? Okay, good. But here's the thing that you also want to keep in mind. Negative 4 times negative 4 is also 16, right? So negative 4 is also the square root of 16. Okay? Does that make sense? Okay? So to indicate that the positive or principal square root is desired, the radical sign, which is what we see here, okay? This is our radical sign. That's referring to the positive square root. Okay? Therefore, the square root of 16 as we see it here is 4, and only 4. Okay? So we're looking for the positives. The expression under a radical sign is what we call that radicand. Okay? So the number 16, when it shows up underneath that radical, is what we call a radicand. So if you see like a word problem where it says the radicand is 25, okay, then what we would be trying to solve for would be 5, okay, because they're telling me by that 25 is underneath a radical symbol. Okay, the radical sign is the radicand. The 16 is a radical expression, and 16 is the radicand. There are roots other than square roots. For example, we can also get cube roots. 2 to the third is 8, so 2 is the cube root of 8. 3 to the fourth is 81, so 3 is the fourth root of 81. Okay, as well as negative 3. Okay, as long as my root is an even number, I can have a positive or negative to that. Okay. Okay. All right. Yeah, I think that's so. I'm trying to think of the best way to word that. All right. So in roots. Okay. Given that a and b are real numbers and n is an integer greater than 1, if we had a to the n, so a to the nth power equaled b, then a is the root. Is the nth root of b. Okay, given that a and b are not negative and n is an even integer greater than 1, or given that a and b are real numbers and a is an odd number and n is an odd integer greater than 1, if a to the n equals b, then the nth root of b equals a. And all that's kind of confusing. I mean, it sounds really bad when you read it, right? And when you read it out loud, you're like, that just doesn't make any sense. Hopefully make more sense as we look at some questions. So the product rule for radicals. Okay, given that a and b, and I really wish that they would throw in a few more real numbers. Fortunately, they do a little down further. So given that a and b are real numbers, so if in a radical I have two numbers being multiplied inside of it, okay, and I've got the nth root, I can split those two things up and get the nth root of one times the nth root of the other. Okay? The product rule states that the square root of 10 can just as easily be written as the square root of 2 times the square root of 5. Okay? So this rule is helpful when one of the radicals is the product can be simplified. For instance, if I have the square root of 20, I can break those things down into other multiples. Okay? Or factors, sorry. So 20 can be broken down into 4 and 5. So the square root of 4 times the square root of 5 is the square root of 20. The nice thing about the square root of 4 is, what's the square root of 4? 2. So that simplifies to be 2 on the outside, 5, I still have a radical 5 because that radical 5 doesn't have a nice neat root number. So the square root of 20 simplifies to be 2 radical 5. Okay, and there's other ways to do that. Okay, that concept can be extended also to variables, assuming that x is also positive. So if I have x to the 6th, then I want the square root of x to the 6th. Keep in mind that just this square root by itself has an invisible 2. Okay, we start to see those numbers actually show up when it's anything other than 2, like the cube root or the 4th root or the 5th root, right? Then that number has to be there. But until then, we're talking about 2, the square root. So The square root of x to the sixth could be written as the square root of x squared times the square root of x squared times the square root of x squared. Okay? Well, the square root of x squared, the square root and the 2 exponent cancel each other out. So that's going to leave me with x. So this equals x, and this equals x, and this equals x. X times x times x is x cubed. Another easier way to think about this is through division. Okay? If I've got a variable with an exponent in here, I'm always going to divide that exponent by the root number. Okay, so what's 6 divided by 2? 3. I get x cubed. Okay, either way that you think about it, okay, hopefully is going to be fine. So if I've got x to the fifth, I can work it out and I can expand it like that, or I can take 5 and divide it by what? No. What's the root number? 2. So 5 divided by 2. Right? 5 halves. But notice that in this case they want it even, right? So x to the 5 halves is the same thing as the square root of x to the fifth. The exact same thing. But I break it down like this where I get 2 times 2, or sorry, 2, 2, and 1. Okay? I'm getting some confused faces. Do we understand that? You do? Okay. So this is 2, this up here is 2 plus 2 plus 2 is 6. Down here, 2 plus 2 plus 1 is 5. The square root of x squared is x. The square root of x squared is x. This won't go out. Right, it just stays. Okay? So really, and this is probably a mistake on my part, that should be square root there. So x times x is x squared with the square root of x. That's how I'm getting this answer. All right? And we have types of real roots. Like I said, here, where my square root is 2 and my exponent is n, I can take that out and get x to the n divided by 2. Right? Just like I could have gotten x to the 5 halves. Okay? As an alternative to x squared times square root of x. Okay? If n is odd, right? So let's say that this was like a 3 or something like that. That's going to be n minus 1 divided by 2 times the square root of x. That's a lot more confusing than it needs to be, and it'd be a lot easier if we had real numbers that I could show you with it. For instance, let's say we had the square root of x cubed. Okay, that's an odd number. All right, so what they're saying is that would be 3 minus 1, 2 over, so that's giving you what, 2 over 2 times the square root of itself. So you could look at this as x to the 3 halves, or, what is that? That's also square root of x squared times square root of x, right? So that's going to be x radical x, which is what they're showing. Everybody confused yet? I want to get everybody nice and lost. Okay. All right. When radical expressions have the same radicand and root, they're what we call like radicals. They become like terms. Okay? That square root begins to act, that whole square root begins to act like a variable. Okay? And they can be combined. Like I said, like combining like terms. So 2x plus 3x plus, or 2x plus 3x equals 5x. Well, 2 radical x plus 3 radical x is 5 radical x. Okay? It works just like a like term. All right. I think that's probably, nope, we have more. Great. This is a long, is it the last one? So sometimes radical expressions do show up in fractions, and a radical expression is not considered simplified if there's a radical in the denominator. Okay? Radicals are, however, allowed in the numerator. That's not a problem. So what we do next is what we call rationalizing the denominator, and this is the part that will follow you around and you'll need to be able to do. So if I have something like 6 radical 2, I don't want to change the value, but I do want to change the form of it. And the way that you change the form of a fraction without changing the value of a fraction is you multiply that fraction by a fraction that's equivalent to 1. Okay? Because if I multiply something by 1, I continue to get the same value, although maybe in a different format. So what I'm going to do is I'm going to multiply by the radical that's in the denominator over the radical that's in the denominator. So if I have 6 over radical 2, I'm going to multiply by radical 2 over radical 2. Does that make sense? Yeah. Because this is equal to 1. Yeah. All right, so 6 times radical 2 is 6 radical 2. Radical 2 times radical 2 is radical 4. Okay? Well, square root of 4 will simplify to be 2. And I'm going to give you a great big hint here. Anytime I multiply a radical by the same radical, the result is the radicand number. Okay? Every time. So if I had square root of 3 times square root of 3, that would equal square root of 9. What's the square root of 9? 3. Square root of 4 times square root of 4 is square root of 16. What's the square root of 16? I could keep doing this all day. All right? What I want you to understand is that square root of 4 times square root of 4 is 4. Okay? Is that simple enough? All right. So that simplifies to 2. I get 6 radical 2 divided by 2, but 6 will divide by 2. And so I wind up with 3 radical 2. And that's rationalizing the denominator. So when the denominator is a sum or difference, okay, meaning that I have a square root, but there's an addition or subtraction in that denominator as well, we multiply both numerators and denominator by the conjugate of the denominator. The conjugate, let's say I had, for instance, let's say that this was square root of 2 plus 1 down here. Okay, where the plus 1 is on the outside. Okay, the conjugate would be not just square root of 2, but square root of 2 minus 1, square root of 2 minus 1. And I would multiply both the numerator and the denominator by the conjugate. The conjugate is exactly what I have, except with the opposite sign taking place between those two. So it's the opposite operation. So if it's addition in here, it becomes subtraction over here. If it's subtraction over here, it becomes addition in the conjugate. Okay? The product of radical conjugates does not contain radicals because what I just explained to you is that anytime I'm multiplying that radical by its like radical, which cancels out the radical. All right, I can tell we need to get into some questions. All right, square root of 27 times square root of 3. Okay, there's a lot of different ways to do this, but once it's simplified. So one way we could do it is just 27 times 3. What's 27 times 3? 81. Somebody know what the square root of 81 is? 9. Okay? Another way that you could look at this is 27. 27 breaks down as 3 and 9, 3 and 3, right? Which means the simplified radical form of square root of 27 is 3 radical 3 times radical 3, right? Okay, well what's radical 3 times radical 3? No, what? Well, yeah, radical 9. What's square root of? So that would give me 3 radical 9 then, right? Well, what's radical 9? So what's 3 times 3? Do I still get 9? The first one might be easier though, okay? But I'm saying that there's more than one way to get there. All right, cube root of negative 8. Cube root of negative 8. Let's see. Let's go ahead and look. Negative 2, you say? Oh. Negative 2. Good job. Okay. All right, let's, I do want to look at a conjugate question here real quick. You'll see with number 5 is a conjugate question. So I'm going to multiply by radical 7 minus radical 2 over radical 7 minus radical 2. Okay? I get 9 times radical 7, which is 9 radical 7. 9 times negative radical 2 is negative 9 radical 2. Down here, I'm foiling. So radical 7 times radical 7 is? No. 7 times 7. What's the square root of 49? 7. Okay? Right? Because it's a sum difference, I only have to do the first and the outer. Okay? Square root of 2 times negative square root of 2. Okay, well, what's the square root of 4? 2. So, but I'm getting a minus 2. So I actually get 9 radical 7 minus 9 radical 2 over 5. Let's check that answer. Number 5. Okay. All right, from here, let's look at some actual homework problems. Okay, so that we're not getting too far off into the weeds. Cover something that you actually need. Let's see. Why don't you pick something out of somewhere between A and M. A and M. M? So what you said, M? Huh? It says A through I on the board. Okay, well, mine only has A through N, so. Oh, okay, you said it shows A through I? Okay, all right, give me something A through I. H. Okay, H. We got the negative 4th root of y plus 2 square root of y minus 7 4th root of y minus square root of y. Okay. Let's see. What I would do is I would get these things, so pull these out of the radical. Do we understand how I did that? Got y to the 1, negative y to the 1/4. Does anybody not understand? Because this has a 1 exponent. 1 divided by 4 is 1/4. Plus 2 y to the 1/2. Right? Because there's a 1 there and a 2 there. Minus 7 y to the what? 1/4 minus y to the 1/2. Now, if you'll remember, I can only combine terms where the exponent is the same, right? The coefficient doesn't have to be the same. The variable and the exponent has to be the same. So this negative y to the 1/4, does it have a like term with anything? With the negative 7, right? So what's negative 1 minus 7? Negative 8. Y to the 1/4, right? Okay. And really, I think that they're, well, I'll explain here in a second. Let's see. So that gets this and this. And then I got the 2 and a negative 1, right? So it's just giving me positive 1, y to the 1/2. Now, they actually are looking for something quite a bit easier, that your like terms are actually already here. We didn't actually even have to change forms on anything, because their answer that they're giving you is negative 8 4th root of y plus square root of y, which is just the radical form of those things. So all I really had to do was combine like terms up here. Does that make sense? Okay. So we probably made that a lot more complicated than it needed to be. Pick another one, yeah. Yeah. All right, pick another question. We got some time. I. Okay, so square root of 50 minus square root of 32. Okay. Square root of 50 minus square root of 32. Okay, what I would do is I would simply, Well, that's my I. Okay, why don't you tell me what I says? I is a word problem. Is it the radius of a circle? Oh gosh, I don't even have that question. Am I in the right? I'm in the right book. Lesson 40, right? All right, I may have to. Let me use your Chromebook. Okay. Because yeah, I don't even have that question. Refer to the formula in example 5. If a pendulum makes a complete swing in square root of 2 pi to the fourth times the fourth root of 2 seconds. Right, a simplified expression for the length of the pendulum. All right, so we do need example 5 to go from. All right, the length of a pendulum is given by this equation. Length equals 8s squared over pi squared. So we've got that where L is the length in feet and S is the time in seconds. So this is my time in seconds, right? All right, so we've got to do that first to simplify my time in seconds. Well, possibly. So, all right. Okay, so let's look at this. The square root of pi squared. Okay, that's going to be pi squared, right? Because 4 divided by 2. Does that make sense? So pi squared 2, square root of 2 doesn't simplify. Okay, you can't pull that out, right? And times the, let's see, it would be 2 to the 1/4. Make sure. Times 2 to the 1/4. Okay, so that looks like my seconds a little different than what they have in their explanation. It'd be easier if ours looked like theirs. Okay. Eric, you'd help me out with ceasing on the tap in there. Okay. All right, well, let's try this. 8 times pi squared square root of 2 times 2 to the 1/4 over pi squared. The problem is that I won't be able to even know. I'm going to go ahead and hit pause on the video just because there's kind of like these awkward silences. I may just end it and see if I can't figure it out.